Okay, let's give Brett and Linda our attention here. They're doing mathematics in flight. Da-da-da-da-da-da-da.
Good afternoon. We hope to keep you enlivened right up till the very end.
Our title is nice and short.
Easy to spell, pretty much. Sorry. Yeah, we're mathematics in flight. Of course, flight as in happy flight, not leaving places. We are Brett Carlson and myself, Linda Peters. We both teach at Jefferson in Rockford, Illinois. And we are part of the four from Illinois, for those of you that haven't been with us every day. And we both teach math. I'll be teaching Algebra 2 this fall in some co-taught classes because of the background in special ed. I like working with them, as well as the so-called regular kids. Grades 10 through 12 will be typical, and Brett will teach college algebra, grades 10 through 12 also. Our mentor was Savita Verma. Our mentor's research area is in two fantastic acronyms, TT Safe and TAPPER. Mentor's research is in both, and the paper we admired and saw before we got here was having to do with closely spaced runways, especially San Francisco, and optimizing the flow of aircraft and keeping the safety right up there where we expect it. No small task.
So as far as our main focus on our lesson, I'll try to go through that fairly quickly, but the application of mathematics to air control flight patterns in the final stages of flight, optimizing the use of the airspace, time, and fuel while maintaining exceptional safety standards. Students will view an interview with Savvy, and through a series of STEM-based activities, including a construction of a model airplane, the Smart Static Simulator, and a student application of modeling, the students will gain an understanding of how modeling and simulation is essential and effective and safe to safe air traffic flow. And in addition, to enhance their knowledge and critical thinking skills, they'll have an opportunity to play a game that we are developing, like a board game, and where they kind of play around with the different things that happen on their way to a terminal. And another thought is to have them come up with a game too. But prerequisites, basically Algebra 1 knowledge, and the stuff we're going to be doing is kind of a process as we go through our subject matter, and so we're kind of going to be teaching as we go through our material. We hit a lot of Common Core standards. I point out just the Common Core standards because our school is really pushing the use of these, knowing that they're going to be there, and we want to kind of be ahead of the game. And so I didn't list out the national standards and our state standards because our school is really just pushing towards the Common Core standards. And so we've got quite a few here, as you can see, and one more. So we've hit quite a few Common Core standards by doing this lesson, this unit. Learning objectives, students are going to work collaboratively in teams, keep accurate records, make predictions, like Carrie was saying, make predictions, track data, analyze, and come up with a conclusion. Complex problem solving, distance equals rate times time, multi-step conversions, using circumference, graphing linear equations, systems of equations, and also piecewise functions. I didn't list that here. Apply Pythagorean theorem to various aspects of flight. Manipulate systems of equations to determine potential collision points, and also locate air traffic paths on a road map. Piecewise functions. Associate mathematical terminology to aeronautics, higher order critical thinking skills, solve and apply literal equations, operate the Smart Sky simulator, connect math to the real world. Again, doing simultaneous distance rate times time problems, like was shown up here on the board. Compare and contrast experimental data with simulated data, make quantitative measurements and calculations, and explore STEM careers and opportunities. And yes, you're going to explode your brain. But of course, we always want to have fun while we're doing it. Otherwise, it gets boring. So the procedure, basically, we're going to start out. We're going to show a video that we have on the Bell XV15. Won't show the video. Just want to make sure we address it. But basically, in this video, it gives these students an idea of thinking outside the box. You know, okay, you know, they took an airplane, they took a helicopter, and they wanted to put them together. Kind of like they do with cars a little bit, with the hybrids and things like that. They do with bikes, with a road bike and mountain bike, they make the hybrid there. Okay? Get them thinking, okay, there's a lot of different things you could do. And it's a really neat video where kind of it'll capture their interest and they'll be kind of like, ooh, wow, that's really neat, and get them excited about it. And then we're going to talk about the busy skies. You know, we've seen the 24 hours of flight. And in fact, the one that we have actually shows at the end some weather patterns involved and how the flight changes, and you see these planes doing these little circles because they have to wait around the weather. It's pretty funny. So that's going to be incorporated in when we work with our, you know, having to make decisions on their approach to the terminal. This was actually in Minnesota, this runway. But the procedure here, this is starting out after we talk about air traffic and how busy it is, and the whole procedure with you know, having to land and Savvy's focus. This here is the linear compression where they have to get in line and get as close to each other without breaking a safe distance. And so we're going to work on that and have them do some distance rate time problems where, okay, you break that barrier, you're within 3 miles, 4 miles, 5 miles, or 6 miles, depending on the aircraft. And air traffic says you need to correct that within 30 seconds. And they have to adjust their speed, and they have to know what speed is going to achieve that safe distance within the 30 seconds. And so then we're going to, you know, play around with different types of problems where they have to be able to work with that situation or scenarios that's given to them. And then we're going to have them you know, explore distance, rate, and time with a model airplane. You know, we've got actually this exact plane here we're going to demonstrate for you. And we've got some data sheets that they're going to work through and fill in the charts. And I've got an example here that I'll pass out to you. And I'm going to have Myron and Judy come on up to demonstrate the actual flight of the model. Careful.
Before I leave Ames. Okay.
And then what I'd like to have is some people in the here at the tables participate in timing. And Kevin, you can do the timing. And have someone maybe, would anybody like to volunteer to identify when the plane takes off the ground and lands, and count? Anybody want to volunteer to do that? George?
I've heard you count before.
Would you like to do that?
Okay.
All right. So basically, the students, they will be actually building the planes. One of the things that while they're setting up here, I'll explain what I'm going to have them do. Did everybody get a sheet?
No, I didn't, Brett.
Okay.
It's a plaque giver. I think Pat needs it too. Thank you, sir.
Am I going to start the watch if you tell me it's up, and then what do you want me counting?
Yeah. time the actual flight. So up,
So as soon as they-
up and land,
And
yes.
we just land on top.
Yes.
And you're gonna count them in the left.
Right.
Yeah.
So what we have is, I've instructed them how to set up the plane, and there's a video that the students would watch, and it kind of talks them through how to do this and how many number of turns to do. But I've modified what they do on the Aerolab video. They recommend 1,000 turns, okay? And this is a special competition rubber that is being used here. Don't forget to pinch it and let it spin. All right, he's done. So what we're going to have is different groups are going to be assigned the number of windings that they're going to do. One group will do 600, one group will do 800, one group will do 1,000. And they're going to do 3 sets of trials. First set of trials is going to be when the wings are at the front of, there's like the slot for the wings, they're pushed all the way forward. They're going to do 3 trials. And then they're going to put the wings in the middle, do 3 trials, and then the wings at the back and do 3 trials. And what's going to happen is they're going to ask themselves what they're going to predict what they think is going to happen based on the wing placement. Okay? And the different groups are doing a different number of spins. So when they're all done with their activity and their data, they're going to have to go talk to each other and find out, okay, you had this number of spins, what kind of data did you get? And then based on that, they're going to work and talk about and analyze the data and summarize what they observed. So what they're going to do here is she's going to place it on the ground. I'm going to have you're fine. So she's like at 12 o'clock, okay? Obviously it's going that way, so you could say 9 o'clock, 6 o'clock, 3 o'clock, or anywhere in there.
But I'm counting how many times it makes it past 12 o'clock.
From the point where it takes off the ground. So you have to pay attention to where it takes off the ground. Right. And one of the things that you got to point out to the students is that you want the plane to be pointing out a little bit towards the outside of the circle. Otherwise, it's going to run into the garbage can. And you're going to have to get up and move pretty quickly. So, are you ready, Kevin?
Get the cameras ready.
George? All right. Go ahead.
Let the propeller go first.
Oh, yeah,
right?
let the propeller go first. Let it get spinning and then let it go. Go. Uh-oh. Oh!
1! 2. 1.5.
Okay. Obviously, you need to make sure you have the room. So here we go. Ready to start over?
Yeah, go.
Kevin?
Yes.
Okay.
There you go. That's what it should look like.
We figured this was pretty much the minimum, or actually maximum distance we could accomplish in a classroom. And even this will be quite a production.
Right there. So, 14 by 0.4
Yeah.
or 5.
Yeah, a little bit over 14. But
Okay.
how much?
It didn't take off from over here?
No, it took off from over here.
Oh, it did? Okay,
Yeah, it
so
was going
14.
a little bit, but then
I
took
got
off
you.
from here.
All right, all right.
And the radius was about 1/2 that yesterday, and one of the first things we noticed was it made more noise.
Yeah.
So that became an interesting
So how
puzzle.
long did it take? That's what it should look like.
20.05 seconds.
20?
20.05.
20.05 seconds. And so on your sheets here, you could say 14 laps. The distance on that we already had measured out to be 1 meter. And so 14,
The total diameter.
and it was 20.05. The number of windings was 1,000 minus however many. The takeoff was what, like 50, 75% around? It went around 75% of the circle before it took off.
Oh, yeah.
Yeah, so that's where we would have recorded it, because it
Yeah.
started here, it
Right.
went all the way over to here
Right.
before it took off. So it went around 75% of the circle. And then it landed right around that 75. And so it was pretty much straightforward. And then based on that, you up here with the radius, it's 1 meter. So they would have calculated the circumference, and they would work out and figure out their average speed based on the equation that got chopped off of your paper. But its average speed is distance over time. So the average number of laps. So this one was 14. The next one might be 13.25. The next one might be 13.75. So they average those together, and they get the number of laps for the trials over the average number of seconds, maybe 20, maybe 19, maybe 19 and a half. And then they figure out their speed. And we are going to then have them do conversion to knots. So they'll convert all that, and we'll see how fast that plane is flying compared to the real planes. Hopefully that was fun. So and then an extension, after we did that activity, explored distance, rate, and time, and we actually determined that would probably take a couple days because they would build the airplanes, do one or get partway through their trials, finish up their trials, and then be able to converse with the other students that had the different number of windings on their rubber band. So then after that, we would already have shown them these plates, and so they kind of have an idea what they are, and we talk about them a little bit more, so it's not something just all of a sudden it pops up in front of them. But we would talk about the values with the distances between the fixes and the VORs, and so we would say, okay, these airplanes all need to get to this point right here. And they have those safety standards that they need to stay away based on their size of plane and all these other things. So we need to make sure that they get lined up, and they are, for this purpose right now, 3 miles apart. And we would say, okay, well, the black plane is going to follow that path right there. The blue plane is going to follow that path. And then the red plane is going to follow that path. And so they would do some math to try to figure out, okay, the total distance for each of these planes is this. They're all, this one's flying at this speed, this one's flying at this speed, the third one is flying at a different speed. Which one is going to get there first? I'll put them first. And then they're going to figure out, okay, which one would be the best one to go second? Which one would be the best one to go third? And when they're done, they'll see if they got it. Okay? Without any safety collision. So, they're getting that true, real world simulation on paper, where these guys have that big, huge computer monitor screen that they're looking at, and they can say, okay, you need to slow down, speed up, whatever. And then from that, to lead into the smart skies, where they've got workbooks that go along with the different challenges, so they can record their data, they can do the same math that they just worked on, and they could try it out on a simulator, on the computer, and see if they learn from their practice. Along with landing a plane, you have you're going to be decreasing your acceleration so that you're lowering your elevation. And it does take time to do that, right? And so in that, we figure we could teach acceleration, probably more in the college algebra than the Algebra 2. But we could talk about all the aspects. We could talk about the rate of acceleration from one point to the other point in time. We could talk about the average, or the distance from one point to the other point. And there's a lot of different ways to look at this type of flight. And then the other thing, getting towards the end of the unit, this is an activity where they would be given 5 planes, and I say you need to have at least 1 heavy, at least 1 small, and 2 large, who knows. And then they could choose their 5th plane. Or I would say that you have to have at least 1 of each, and then they could choose the other 2. And so based on an approach plate, they would place these out, they would make up their own scenario, okay, this one's flying at this speed. I give them guides. Okay, this one's flying at that speed, this one's at this speed, this one, this one, this one. So they set it up, and then they work through the same kind of concept that they do with the smarts guides, but now they actually have to say, okay, I've got a large one here, so if that gets third in line, I need to go over to this chart over here. I need to figure out my spacing between the planes, the one that's in front and the one that's behind. And so they need to work through this, and they figure out, okay, this is my most effective way, I'm going to get it done. They write it all up, and they're done with that part. Then we're going to have situation cards. And they draw a card, and it says, plane number 3 had wind force that blew him off track, and he had to adjust based on, blew him off course and took him off, or slowed him down to this amount. How does that affect everything? Okay? Does that, now he has to go behind this other plane, and then they have to rework that, and then explain the differences and changes that they made. And I think 1 is probably enough, maybe 2. Because it's a lot of work just to get all that set up for them. And then, as far as the game goes, this is one possibility for the game where they've got the planes coming in from this side and the planes coming in from this side. There's 6 points to get to the terminal, and again they're trying, they're working to get in, and each spot they take a card. The card tells them a situation. Maybe they got blown back, maybe they got blown forward, maybe the air is, everything's going well, they just stay on the same course. Maybe there's a storm in the way and they need to go from this point to this point. So this is a work in progress, but this is just an idea that we had, actually all 4 of us, as far as incorporating this into the whole plan. And an extension, this would be probably a month down the road, where you're working with systems of equations. And some people would like to know where these flight paths are over the land so they could avoid buying a house there. Some would like to know where these are so they can go watch the planes or watch the air show. So basically what we would do is we take the approach plate, we figure out where these lines are, and we calculate some equations, we'd find the intersection point, and then we'd superimpose them onto the map. And then from the map, we would then look at this and have fun with that.
Use Google Earth.
What's that?
Use Google Earth.
Yeah, right. Yeah.
You need to superimpose. Actually, you'll find flight paths on Google Earth.
Oh, okay.
By the way, many of our students live in this neighborhood, and over the years I've heard many people who live on 20th Street make comments about the incredible noise overhead and the low planes.
Our school is right here. Okay, and then getting into piecewise functions, they could take a plate that looks like this, and obviously, I don't know what your knowledge is of piecewise functions, but it's basically different equations at intervals where the lines are different and they change. So you take and you map out, you put a graph over it, you map out your path, and then you're going to have an equation for each of these 5 intervals, and you're going to say the function is this equation between this point and this point. And that would be what they would do for the piecewise functions. And there's a lot they can do with that. They can do that many times to get practiced.
Okay, this assessment resource pages, the constructing airplanes from kits and collecting data, and that really is, we may give them the pieces of paper to record the data, but it's up to the students to record good data and communicate with other students in the room, which I think is essential. Because anybody can collect basic data, but when you have to compare with others, because you did something different than they did, that makes the difference. Distance equals rate times time. in its different forms, using the basic one as well as the slightly more complicated one, and doing problem solving. The Smart Skies, of course. We do have a library with a computer lab, and it's easy to get them there. Graph linear equations. Let's see, systems. And the systems are where, let's say if they want to see an air show plane come in, or 3 or 5, they might, we might agreeably make a system of 3 equations and try to find, where would these planes overlap, but at different times. But that's the person that wants to see the air show planes coming in to the airport. We would rather focus on that than collisions. Systems, piecewise functions, different equation for each segment. And then it makes sense when you have aviation in the mix.
And another addition to this I meant to mention earlier is we have the graphing calculators, and we've got the TI Inspires also, and so we could incorporate, the plan is to incorporate the graphing calculators in this, and I would put in some different variables, and there's a slider in there. They can move the slider to see how it changes the graph, whether it's based on speed, whether it's based on approach, things like that. And so, they can get a really good sense of, what really changes their path and how it changes the path, and gives them that exploration. And basically, the practice that they're going to have going through that, they're going to be recording that and be turning that into us for the assessment. Whoops. Ames 5.
And the data will consist of the recorded revolutions, as we did, the 3 positions of wing placement with predictions and data on that, different rubber band tension, and the 2 greatest distances will be recorded from each class, so I'm sure prizes will be involved. The results of Smart Skies Mod Sim with best times with proper separation. Because I have a feeling there will be quite a few best times, but they may be coming in at creative intervals sometimes. Constructing the airplanes from kits, not every one kid, it's more like 3 or 4 kids to one airplane. Collecting data, again, the collaborative kind of work, also inspired by NASA, the most collaborative place I have ever seen in my life. Connecting the distance formula to aviation rather than merely finding 2 artificial spots to do math on. Using Smart Skies, I think they're really going to like. When I did a little bit of research on simulators online through, I believe it was YouTube, I noticed that there are several simulators online, and lots of people do this recreationally.
Yeah, the gaming.
And they're not even working at an airport, they just like doing sims. So that was nice to find out. And of course graphing, because it couldn't be math unless we're doing some kind of graphing and
You're going
having a
backwards.
grid.
Oh, that's because I went and
This is
I'm still on this thing here.
oh, okay.
There we go.
And then the evaluation, we'll have the application problems about violating separation, the distance formula results, and the homework pages to match those approach plates. We wanted to go creative with Smart Skies and do a little bit of charade or Pictionary style activity. This is in conjunction, every teacher in here has probably done the Hangman review, correct? Where it's vocab word time and, it's Hangman. But I like the charades to make sure that we assimilate the math terms in there and concentrate on them. Maybe mix in the aviation also.
In the workbooks.
In the workbooks. We have evaluation continued with application problems to calculate acceleration. While I will probably show the acceleration formula and the equation that precedes it, showing the change in x equals all the the other form of distance equals rate times time will solve for literal equations. Brett's students will push it on a little further and use it, put in values, I'm sure. Mapping out flight paths after the air traffic control activities, and piecewise function graphs, which I firmly believe my students will enjoy to, change it.
It's one of the things that they always have a hard time understanding, and I think this is really something that'll help them put it together with something real. You always use the postage stamp and the weight of the box and all that, but they just don't understand it. But the main idea here is that, almost every lesson or every day that we're doing something, there's going to be data, there's going to be work and written work and things like that that we're going to be gathering.
And to spread the word. Like many others, we'll teach this earlier in the year. Some of it we're going to have to make a piecewise function because of our curriculum demands. So I will let them know right on day one, because of the NASA experience, we will have a definite aviation/space theme going throughout the year. And some of these activities won't be one day right after the other, but they will be dovetailed nicely right into our curriculum. And our partner, Hamilton Sunstrand, has wind tunnels, so we will be happy to call them. Hamilton Sunstrand has a history of, even way before this project, of sending their engineers over to help in the tutorial center. So our students are used to talking to engineers and getting all sorts of wonderful help, something I had never heard of before in my experience of going to school. So Hamilton is not just a casual partner. They've been working with us for years right in the tutorial center.
You're going to push for the lab guys, too.
Yeah. And so, and NIU has promised equipment, which of course made our eyes light up. We would like to know what exactly that equipment is. They have welcomed us to our campus, which is only, what, an hour away from Jefferson?
45 minutes. And they have 2 labs that they offered that we could bring the kids to and be able to work in their labs.
So the idea of 2, and Hamilton Sunstrand's even closer, it's right in town. So we have places we can take our kids that don't involve the 3-hour bus ride. It's really nice for our students. Then there's a local children's museum that contacted me, and 2 of the ideas I had that we could collaborate with creating an exhibit already at the Children's Museum. If you've been to a children's museum ever, you know that there's all sorts of hands-on science, physics, basic Newton law going on. So we could collaborate with helping to inspire an exhibit.
And with that, have set up a thing where our high school kids work with the younger kids on some of the different maybe modeling and just an activity.
They also have a rocketry class, which I took. So, when we made our rockets, it was a quick reminder to make sure absolutely that the nose cone is on straight. Because when I really looked at it, I thought, oh no, it's going to look cute, but we don't want to watch it fly immediately. We need a nose conectomy in some spots there. So the rocket class, I think, would be a great place for any of us to show up and help inspire, because the people that take this rocket class are typically educators. They could be anybody in the community, but it's often the teachers that are at these classes. So there's another nice teacher exposure. Neon, of course, sharing on there. We have a Blastastic in our school system, so anytime you have good news, you just email that one person and she puts it all on Blastastic. At the next institute, we will be able to speak. We have a SharePoint, a website where we can keep colleagues informed.
And maybe, the idea of some of the websites and things that we've learned as well.
And we do have at Jefferson, we have the shared drive where anybody can just go in and see what anybody's doing. So that's another easy place to share, which I just mentioned up there. The other ways to spread is, of course, by Facebook, where we have already done some of that. individual accounts. That's another good way to do that.
We've already connected with NASA Ames Research Center and the Loral Space Systems.
And we have math and science, of course, have a really nice collaborative history at Jefferson. So we will have absolutely no problem sharing with all of our science teachers. One who is a major NASA buff, who unfortunately was the 5th person to sign up for this workshop. So, but he's in fact a local expert, and he is very, very knowledgeable on rockets and anything NASA. So that's, we really, as you can see, we're determined to spread the word. We have, of course, memberships in the NIATM.
Right,
They
yeah,
have the business,
which was mentioned.
where they have the,
Judy and Myra.
right, we didn't want to
Same stuff.
do the complete redo of that. Any questions?